Hi, welcome to my topic Circuits and Networks. I am Ravikant Mallajoshila, and in today's class, that is in class 5, we are going to end up with all the Thevenin's theorem related problems. The basics of Thevenin's theorem, the numericals based on Thevenin's theorem, and the Thevenin's theorem with the different dependent sources are being covered from class 1 to class 5 under Thevenin's theorem. And in today's class, we are going to see how to obtain a particular Thevenin's equivalent circuit for a given network or a circuit. For that, let us start with this problem. Here you can see we have to obtain Thevenin's equivalent network across XY terminal. So you can see here we have 4I1, which is called as current controlled current source or current dependent current source. This current I1, 4I1, this I1 is flowing in 12 volts in series with 6 ohms, and that is the challenging current which is going to challenge this dependent current source. So let us start with the solution. As I told you, we have this dependent current source which is called as current controlled current source. This is the abbreviation. So we need to find out the Thevenin's equivalent network, that is this particular network for this given network. So we have to find out open circuit voltage, which is called as Thevenin's voltage, and we need to find out Thevenin's resistance. Here Thevenin resistance is a special technique where we have to find out the open circuit voltage by the short circuit current. How do we do that? So these are the terminals where we need to find out the Thevenin's voltage and resistance. Let us go with step-by-step process. So first, I have taken this circuit and I'm trying to find out the open circuit voltage. The open circuit voltage, it is found over here. So you can see this X terminal and Y terminal are in fact shifted across 4I1 in this fashion. So I'm assuming the measurement, the upper plate positive and the lower plate as negative. When this current is flowing 4I1 in this closed circuit, then naturally we are going to obtain the open circuit voltage across 4I1, which is depending upon the current I1 in this fashion. Now you can see the given current, that is the branch current direction I1, it is in this fashion, which is shown by the red arrow, and to this branch current, this dependent current source is flowing in opposite direction. In fact, I1 is equal to minus 4I1. If this is true, then that will be equal to I1 is equal to 0 amperes. So I1 is equal to 0 amperes because we have I1 plus 4I1 is equal to 0, which gives the result as I1 is equal to 0. So current is open circuited. Now the same current is going to flow in 6 ohms. The same current is going to flow in 6 ohms. So 6 multiplied with current I1, that is 0 amperes, making the voltage to be 0 volts. When the voltage across this terminal is 0, the so-called resistance can be replaced by a short circuit. Now when can be replaced by a short circuit, now the given circuit is reduced to this fashion. With this, we have open circuit and short circuit at these terminals, which makes VOC is equal to, directly you can see the measurement, which is equal to 12 volts. Now once we obtain the value of open circuit voltage, which is also called as Thevenin's voltage, let us find out the Thevenin's resistance. For finding out Thevenin's resistance, already we have estimated VOC is equal to 12 volts, and we know that Thevenin's resistance is equal to open circuit voltage by short circuit current. So we need to find out short circuit across XY terminal. So short circuit across XY terminal resembles this circuit for the given circuit. So if that is true, let me take the loop currents as IA, IB, where IB minus IA according to the supermesh analysis equal to 4I1. You can see IB direction is along with the dependent current source direction. That's why it is IB minus IA is equal to 4I1. So this is a one kind of super mesh because the current source is being shared by two loops. From the given or obtained circuit, what we call the loop current IA is equal to the branch current I1 whereas the loop current IB, which is equal to the short circuit current. Now this is the conclusion what we can inspect by looking at the closed circuit, right? Now with this, I'm framing the equation by rearranging this IB with I1 and IA. So IB is equal to 5 IA, take it as equation 1, and take the other components of supermesh, that is minus 12 plus 6 I1, and this circuit gets closed. So minus 12 plus 6 I1 equal to 0. With this, I1 equal to 2 amperes. When I1 is equal to 2 amperes, IA is also equal to 2 amperes. Once we obtain the value of I1, which is equal to IA, which is equal to 2 amperes, we can easily obtain the value of IB, which is equal to 5 into 2, that is 10 amperes. In fact, this current is the short circuit current. I hope you understand this point. Now, once we obtain the short circuit current, we have resistance, which is equal to open circuit voltage by short circuit current. So this gives the value of Thevenin's resistance as 1.2 ohms. Once we obtain the value of Thevenin's resistance, we can easily obtain the Thevenin's equivalent circuit or network in this fashion. Now, the Thevenin's voltage is 12 and the resistance is 1.2 ohms. So thereby this is called as Thevenin's equivalent network for the given circuit. Step by step, it's an easy process. Please follow these tips to obtain the Thevenin's equivalent circuit. Especially in competitive exams, you'll be asking to find out the Thevenin's equivalent network for the given network. And this is how you have to solve the problem. Let us go with another example. Here we need to calculate Vx and draw the Thevenin's equivalent network across xy. Okay, so you can clearly see it is mentioned here 0.1 Vx. So it indicates it's a current source, but it's a voltage dependent current source, and the voltage is Vx, which is measured over this terminal. So first point, by inspecting the circuit, we have to understand that it's a voltage controlled current source. For that, the Thevenin's equivalent resembles like this. So we need to find out open circuit voltage and Thevenin's resistance. So like the steps we have followed for the previous problem, the same steps we are going to follow for this problem. So first, I'm going to take the circuit as it is, and with clear inspection you can see whether it is XY voltage are called as Vx, which is equal to Thevenin's voltage, that is Vt, or it is also called as open circuit voltage, which is Voc. So this is the clear observation you have to make. Okay. Now, before going to this circuit, when you look at this circuit, this 2 ohms, when it is open circuited, this 2 ohms becomes dummy. When this 2 ohms becomes dummy, you have this single loop circuit. So that is a single loop circuit over here, and we know that the Vx is a measurement across this terminal. So when I'm going to apply current I to this closed circuit, like in the previous problem, I is equal to minus 0.1 Vx. This is the voltage dependent current source. Its direction is quite opposite to the assumed current direction. So I is equal to minus 0.1 Vx. This I'm framing as equation 1. Now applying KVL to the above loop, practically I have voltage 4 volts. I can have a drop across 2, and I have a open circuit voltage across this terminal. So applying KVL to the above loop, minus 4 plus 2I plus Vx equal to 0. This I am framing as equation 2. Once equation 1 and 2 are framed, substitute equation 1 and equation 2, we get minus 4 plus 2 times of I is nothing but minus 0.1 Vx. Substitute the value, then I'm going to get the value of Vx to be 5 volts. This is a small mistake over here. Please observe, it should be 5 volts. It's not 5 ohms, it should be 5 volts. Okay, so this I'm taking as equation 3. Equation 3 is nothing but Vx is equal to 5 volts. This is a small mistake done over this PPT. Please ignore. Now, once open circuit voltage is done, that is Vx is done, we have to find out the short circuit current. And remember, once this terminal is short circuited, when this is short circuited, it is indicated that the open circuit voltage is shorted. When open circuit voltage is shorted, Vx is equal to 0. And when this short circuit conditions exist, then this zero point 0.1 Vx, which is the voltage dependent current source, Vx multiplied with zero point 0.1 will give you the value as 0. Now this 0 is going to be applicable over here, and 0 multiplied with zero point 0.1 makes this current source to be open circuited. So the voltage dependent current source becomes open circuit, and this is how the circuit looks like. Now this is removed and the rest of the circuit is like this. So the rest of the circuit is making the current to flow in this closed loop, that is the short circuit current. That short circuit current, by applying KVL, you can get -4 plus 4, I short circuit is equal to 0, or you can make I short circuit is equal to 1 ampere. This is simple. Now for the given circuit, we have found that Vx is equal to 5 volts. The so-called mistake is being rectified over here. So VOC or Vthevenins or Vx is equal to 5 volts, and I short circuit is 1 ampere. Therefore, applying Thevenin's resistance formula, we are going to obtain the value of Thevenin's resistance is equal to 5 ohms. Therefore, we have obtained VOC and R Thevenins. Then I'm going to substitute this values over this equivalent network, that is Thevenin's equivalent network, like this: 5 volts in series with 5 ohms. Therefore, this is the Thevenin's equivalent network for the given network. So you can see we have seen current controlled current source and voltage controlled current source problems in this particular case. And in my previous classes, we have seen different examples of dependent sources. So this is how we solve a Thevenin's equivalent circuit or network problem for the given circuit or a network. So I hope you like this video. Please share this kind of videos to your friends whenever it is technically needed. And please subscribe to my channel for the future notifications. And please press the bell icon also, as I told you, for the future notifications. Thank you.